When I first opened the telemetry data from China's Tianwen-1 probe, I didn't expect it to feel so personal. Yet the numbers on that screen weren't just values, they were voices, distant whispers carried across millions of kilometers, telling us something extraordinary was happening beyond Mars. It wasn't just another comet or asteroid. It was 3I divided by Atlas, the third interstellar object ever observed by humankind in Tianwen. One had just given us a new perspective no one had seen before. For the first time in history, data on an interstellar visitor wasn't coming solely from NASA or ESA, but from a Chinese spacecraft orbiting the red planet. The idea itself felt poetic, a machine built to explore Mars, now turning its gaze toward a traveler from another star. From its orbit roughly 30 million kilometers away, Tianwen-1's high-resolution cameras began capturing light from 3I divided by Atlas with a clarity impossible to achieve from Earth. Mars's thin atmosphere, its distant vantage point, and its quiet skies created the perfect window for observation. What it revealed has already begun rewriting how we understand matter near a star. Through the stillness of interplanetary space, 3I divided by Atlas appeared not as a fuzzy speck, but as a world of contrasts, shimmering reflections and shadows locked together like the surface of cracked glass. In those first images, scientists noticed something odd. The object wasn't behaving like a typical comet. It was emitting faint traces of water vapor, even while far beyond the region where ice is supposed to evaporate. That shouldn't be possible. Out there, sunlight is weak, temperatures are cruelly low, and yet the spectrum told us hydrogen, oxygen, and faint signs of ionization. This wasn't the first time an interstellar object had defied expectations. Years earlier, Oumuamua, the first of its kind, had streaked through our system, moving too fast, accelerating in ways gravity couldn't explain. Some called it a rock, some an alien probe. No one could prove either. Then came 2I divided by Borisov, a model of normality, a traditional comet, icy and predictable, reassuringly ordinary. Astronomers thought the mystery was over. The universe, it seemed, had balanced its own strangeness with familiarity until now. 3I divided by Atlas arrived like a paradox born between those two stories. It had Borisov's chemistry but Oumuamua's rebellion. It glowed like a comet, yet refused to follow cometary rules. Every observation deepened the mystery. Its trajectory precise, its rotation stable, its emissions inconsistent with what physics would predict. It seemed to belong to both categories and neither. When Tianwen-1 turned its instruments toward it, the mystery thickened. The probe's optics, originally built for mapping Martian dunes and dust storms, were reprogrammed by engineers back on Earth. Those men and women sitting in control rooms in Beijing didn't just redirect the spacecraft. They redefined its purpose. For the first time, a planetary orbiter became a deep space telescope. With adaptive tracking, it followed 3I divided by Atlas across the star-studded background, compensating perfectly for its motion. The result: images sharp enough to expose micro variations in brightness, subtle ripples of reflected light that hinted at something astonishing. The object's albedo, or surface reflectivity, wasn't constant. Certain patches gleamed almost like mirrors, while others absorbed light entirely, as if made of carbon soot. That contrast, crystalline brightness beside absolute darkness, shouldn't exist naturally on an ancient body that spent eons adrift among the stars. Such duality suggests heat, melting, differentiation processes that belong to planets, not cosmic debris. Under normal circumstances, a body wandering through interstellar space for millions of years would be evenly frozen, its surface smoothed by radiation and time. But 3I divided by Atlas looked fractured, as if once molten and suddenly cooled frozen mid-transformation. That strange surface composition raised uncomfortable questions. Could this object be a fragment from the crust of a destroyed planet? Or something even more unnatural, the remains of an engineered structure? Scientists are cautious with words like artificial, but imagination is hard to restrain when confronted with data that refuses to fit any model. Mirror-like reflection on a tumbling fragment, combined with dark carbon-rich layers, calls to mind something manufactured perhaps unintentionally, echoing the glint of a metallic alloy. Yet, perhaps this is just coincidence, a cruel trick of nature designed to test our assumptions. Still, the puzzle wouldn't rest. The light curves obtained by Tianwen, one revealed rhythmic fluctuations, not random, but patterns suggesting a structured geometry beneath the dust. One region seemed to refract sunlight differently, almost as if coated by a thin crystalline film. Another seemed rough, scattering photons irregularly. These clues, small and technical, hint at a history carved by energy far greater than the slow erosion of space. To the teams watching from across the world at NASA's Jet Propulsion Laboratory, at the European Space Agency, at the Chinese National Space Administration, the data inspired both awe and anxiety. What kind of material could survive the violence of interstellar travel and still shine like polished glass? What kind of journey could fuse water-bearing minerals with metallic compounds? Tianwen-1's vantage point allowed something no Earth telescope could match: the geometry of forward-scattered light. In simple terms, it was catching the glow of sunlight, bending through dust, reflecting off microscopic particles around the object. That geometry can reveal the size, shape, and even the microstructure of matter. What the spacecraft saw left researchers speechless. A faint rotating halo enveloping 3I divided by Atlas, stretching tens of thousands of kilometers outward. But unlike any comet tail we've seen, it didn't stream away from the sundae. Instead, it rotated around the object, aligned with its axis like a shell of plasma moving in synchronized motion. If confirmed, this would mark the first known example of a self-stabilizing plasma envelope, a phenomenon unheard of in cometary physics. The implications were staggering. A few hours after the data reached Earth, teams from Harvard, ESA, and CNSA began cross-checking their models. Plasma doesn't behave this way unless influenced by something unseen: magnetic fields, electric currents, or forces beyond our usual grasp. The preliminary conclusion, cautiously phrased, was that we might be witnessing a natural case of magnetohydrodynamic coupling. Plasma shaped and contained not by sunlight or radiation pressure, but by the object's own magnetic field. If that's true, it would mean 3I divided by Atlas isn't just reflecting light, it's interacting with it through magnetic resonance, perhaps even stabilizing its rotation using fields generated deep within. Such a property has never been documented in a comet. It implies that the object's internal composition contains metallic or magnetically conductive material, iron, nickel, or something even stranger. When the Chinese National Space Administration issued its statement, it was brief but profound. Preliminary observations confirm a dynamic ionization structure, unlike any known cometary object. Behind that diplomatic phrasing, scientists across continents understood the real message: something truly extraordinary is happening. In that moment, the boundaries between nations seemed to fade. Across laboratories in Beijing, Boston, Paris, and Tokyo, scientists stared at the same data, the same spectral lines, the same anomalies, and for once, there were no flags, only curiosity. The story of 3, I divided by Atlas, was no longer just about a foreign object visiting our solar system. It was about humanity itself, how we look outward, how we question, and how we listen when the universe whispers through the silence of deep space. As more data flowed in from Tianwen-1, the mystery only deepened. The probe's cameras, originally designed to study the dust storms and canyons of Mars, had now become our window into the unknown. With every new exposure, 3I divided by Atlas seemed to reveal another contradiction. Its surface shimmered with alternating flashes of brightness and darkness, bright enough to suggest crystal, dark enough to swallow starlight. These were not random variations. They formed patterns, as if 2 different materials were woven together across its crust. In Beijing, the mission team noticed subtle shifts in the spectral readings. The peaks were not consistent with pure ice or carbon compounds. They were faint signatures of silicates, minerals altered by water. That finding alone was shocking. Hydrated silicates only form when rock has been in contact with liquid water for long periods of time. But 3I divided by Atlas had spent millions of years adrift in interstellar space, far from any sun or heat source. The presence of such minerals suggested an impossible history, that this object had once belonged to a world with warmth, perhaps even with oceans. More evidence began to align with that idea. Alongside the hydrated silicates were traces of iron-nickel compounds, elements commonly found in the metallic cores of planets and moons that have undergone thermal differentiation. It was becoming clear that 3I divided by Atlas might not be a pristine comet, but a fragment of something far older and more complex, a piece of a planet torn apart in another solar system. The hypothesis sent ripples through the global scientific community. If true, this would be the first tangible evidence of planetary formation and destruction beyond our own Sunday. Somewhere in the vast reaches of another star system, a planet had lived, evolved, and died, scattering fragments like this one across interstellar space. And now, by pure cosmic coincidence, one of those fragments had drifted into our neighborhood. The images from Tianwen-1 showed more than composition. They revealed motion. Surrounding 3I divided by Atlas was that faint, glowing halo plasma moving in synchrony with the object's spin. Every frame confirmed the same phenomenon. The halo did not trail behind, it rotated with it like a protective skin. The implications were staggering. Plasma, when magnetically trapped, can act like a membrane, self-regulating, dynamic, and persistent. The idea that a cometary body could generate such stability defied every known model of physics. In Cambridge, researchers at Harvard's Project Galileo began feeding the Tianwen-1 data into their machine learning systems, neural networks trained to recognize patterns in interstellar spectra. Within hours, the AI flagged something intriguing. The periodic fluctuations in brightness around 3I divided by Atlas followed a harmonic resonance, almost as if modulated. It wasn't proof of anything artificial, but it did suggest a complex interaction between sunlight, magnetic fields, and reflective materials. At NASA's Goddard Space Flight Center, astrophysicists compared the data with readings from the Solar Dynamics Observatory. They discovered faint correlations between solar flare events and variations in the plasma halo. Somehow, 3I divided by Atlas was responding to solar radiation in real time, not passively, but dynamically, as if its internal structure could adjust to changes in electromagnetic conditions. That was the moment the term magnetohydrodynamic coupling began circulating in every lab. It described a state where magnetic fields and ionized gases interact as a single fluid, In theory, it's possible in controlled plasma reactors, but here it was, happening naturally, or so it seemed, around an object from another star. If the object indeed maintained its magnetic alignment across interstellar space, it would have to contain materials capable of retaining magnetization for millions of years, a property unheard of in conventional comets. The question then was obvious. How did it get that way? In Zurich, a group of planetary physicists proposed a bold scenario. 3I divided by Atlas, they said, might be a remnant of a once differentiated planetesimal, a small world that had partially melted under tidal forces before being ejected into space. Its metallic core, frozen in place, could have preserved a magnetic field, while its outer layers fractured and cooled into the irregular shell we now see. The plasma halo, they suggested, might be the result of residual magnetism interacting with solar wind, creating a temporary magnetosphere. As extraordinary as that sounds, it fits the evidence better than any other theory. 3I divided by Atlas would then be the cosmic equivalent of a fossil, not of life, but of geology, a fragment from an alien world whose sun is now just a faint point in the night sky. When the China National Space Administration released its next update, the tone was measured but unmistakable. The statement mentioned a dynamic ionization pattern and a non-classical plasma interaction, terms that even seasoned astrophysicists found thrilling. Beneath the formal language lay a quiet admission. We are seeing something we have never seen before. For the first time in decades, space agencies that had once competed began sharing openly. NASA scientists requested access to Tianwen-1's raw image data. ESA offered ultraviolet analysis from its solar orbiter mission. JAXA contributed magnetometer readings. It was a mosaic of cooperation, a global effort to decode an enigma no single nation could solve alone. And somewhere between the equations and simulations, a deeper realization began to form. The universe was speaking a language all of us could understand: physics, not politics, not ideology, just raw, universal truth written in light, magnetism, and motion. The more we looked, the more the mystery turned personal. If 3I divided by Atlas truly carried minerals altered by liquid water, then it might hold the story of another world, a world that once had its own storms, mountains, and perhaps even oceans. And if such a fragment could survive the violent ejection from its birth system and travel here intact, what else could be wandering among the stars? What other relics of alien geology, or even biology, might be drifting unseen through interstellar space? Late one night, as the combined data streams from the international network came in, one chart caught everyone's attention. The surface reflectivity of 3I divided by Atlas had shifted slightly toward the blue end of the spectrum, a subtle but undeniable change since its passage near the sunday. The simplest explanation: fresh ice, newly exposed or condensed, perhaps triggered by sublimation or internal activity. But that simple explanation was anything but ordinary. It meant that even after billions of years of cosmic radiation, this interstellar fragment was still alive in a chemical sense, reacting, evolving, breathing in the vacuum of space. Somewhere between science and wonder, a question began to echo among the researchers. What if the story of 3I divided by Atlas is not about what it once was, but about what it's still becoming? To every scientist involved, it felt like chasing a living riddle. The data refused to stay still. Each new observation led to more contradictions: magnetic anomalies, shifting albedo, unexplained ion densities. Yet within the chaos, there was order, patterns that seemed to hum with meaning, like a distant symphony carried through the void. And as more nations joined the study, something remarkable happened. The world stopped looking at 3I divided by Atlas as foreign or other. It became ours, a shared mystery, a collective pursuit. For the first time in decades, astronomy wasn't about competition or prestige. It was about connection. It was about humanity's hunger to know, to understand, to stand together under the same cosmic sky. What Tianwen-1 had started from Mars orbit had now become a mirror one, reflecting not only an interstellar traveler, but the best part of what we are, curious, united, and endlessly reaching for answers that might lie beyond the stars. By the time Tianwen-1's final transmission arrived, the world had already changed. The images were clearer, the spectra richer, and yet the feeling they carried was the same as that first moment quiet awe. Somewhere between Mars and the endless dark, 3I divided by Atlas drifted on a shard of another world, reflecting sunlight into the sensors of a machine built by human hands. In that reflection, we saw more than data. We saw ourselves. The collaboration that had begun as a scientific necessity had turned into something far greater. Laboratories in China, the United States, and Europe shared their findings openly, linking their systems in real time. Astronomers who once competed for telescope time now exchanged raw data across continents. What once would have been a political boundary became a bridge. Knowledge was no longer national, it was planetary. And the object itself, silent and unyielding, continued to teach us. As it moved away from the sun, the plasma halo began to thin, but not fade entirely. Instruments recorded a faint but consistent pulse fluctuations in ion density that repeated with each rotation. It was almost as if 3I divided by Atlas carried a heartbeat, a rhythm written in charged particles. The data didn't point to intelligence, yet it carried an undeniable beauty, a natural cadence born from physics alone. The Harvard team refined its models. What they found astonished everyone. The plasma's rotation wasn't random, but synchronized with a magnetic axis that shifted slightly with solar wind. It was a balancing act between chaos and order, a dance of energy that kept the object stable. For something that had traveled across light years of emptiness, its precision felt almost deliberate. Meanwhile, spectroscopic readings confirmed what had only been suspected. 3I divided by Atlas contained not just ice and silicates, but layered strata deposits of materials that once belonged to different geological environments. The object had lived many lives. Once, perhaps, it was part of a crust, then fractured, then exposed to vacuum and radiation, reshaped over eons. Now, passing through our system, it was a fossil of creation itself. At conferences, scientists spoke less about what 3I divided by Atlas was and more about what it meant. If the same physical and chemical patterns that shaped our planets could repeat across the galaxy, then the universe wasn't just vast. It was consistent, predictable, even familiar. The processes that forged Earth were not unique. Somewhere out there, countless other worlds were forming under the same laws, mixing water, rock, and metal in the same cosmic recipe. That realization carried a quiet but profound message. Life, too, might not be an exception. The same chemistry that carved the fingerprints of water into 3I divided by Atlas could also sculpt oceans and atmospheres elsewhere. And if that's true, then existence itself is a repeating equation, not a miracle, but a pattern. Tianwen-1's vantage point had revealed more than structure. It had uncovered meaning. From Mars orbit, the probe had seen the object in forward scattered sunlight, the photons bending and reflecting through dust grains, painting a microportrait of alien matter. For a moment, humanity had achieved something transcendent, a unified glimpse of another world's remains, studied not through competition, but through cooperation. When the Chinese National Space Administration opened part of its dataset to public access, the announcement was met with quiet respect. NASA and ESA analysts downloaded the files within minutes. Independent researchers across the globe began comparing the values. It wasn't about who discovered what. It was about listening to the same voice together. And somewhere within that collective effort, a realization began to take hold. The act of looking outward had united us inwardly. The cosmos had become a mirror. 3. I divided by Atlas was not just a comment. It was a reminder that knowledge itself is the only true form of diplomacy. Months later, the blue shift in the object's reflectivity confirmed that its surface was still chemically active. Fresh ice was forming, condensing, and evaporating in cycles. That subtle shimmer of life-like behavior, not biological, but dynamic, showed that even ancient matter can remain alive in motion. The universe, in its quiet way, never really stops creating. From this discovery came a deeper question. What else lies hidden in the interstellar dark? If a single fragment can teach us this much, what could 100 more reveal? The idea inspired a new generation of missions proposals for deep space probes, Martian-based telescopes, and AI-driven observatories, each one built upon the same principle that Tianwen-1 had proven, that the universe yields its secrets only to those who listen together. In classrooms, students watch the images of 3 I divided by Atlas projected on screens, the faint halo glowing like a ghost of a forgotten world. Professors spoke of its magnetism, its chemistry, its improbable journey. But the lesson went deeper than physics. It was about humility, the realization that our species, small as it is, has learned to reach across planets to study the remnants of another Sunday. When I think back to that first moment, reading the numbers on a screen, feeling the chill of what they implied, I realized it wasn't just about discovery, it was about connection. Every data point, every photon captured by Tianwen-1 carried with it the fingerprints of 100 hands, 1,000 minds, all reaching for the same unknown. The truth, as it turns out, is both simpler and grander than any of us expected. The universe doesn't hide its answers. It reflects them patiently in light and dust, waiting for us to learn how to see. And so 3I, divided by Atlas, continues its journey, a silent traveler, indifferent to our attention, carrying within it the echoes of a world long gone. It will soon leave our system forever, its trajectory taking it back into the black between the stars. But for a brief moment in time, it drew every eye on Earth upward. That, perhaps, is its greatest legacy. Not the data, not the chemistry, but the unity it created. For a fleeting instant, humanity looked at the same point in the sky and felt the same wonder. If someday another interstellar visitor passes through, we'll be ready, not as rivals, but as one civilization beneath one sky. That's what Tianwen-1 and 3, I divided by Atlas, have taught us. That discovery is not just about understanding the universe, but about understanding ourselves. The object is fading now, its brightness diminishing as it slips beyond the orbit of Mars. Soon it will vanish completely, returning to the silence between stars. But the questions it raised will linger, questions about origins, about life, about our place among infinite worlds. And perhaps that's the most beautiful part of all. The universe doesn't just answer us, it invites us to keep asking.